Strings and pulleys are some of the elements that show up more frequently in physics problems, so why don't we take a look at them. Suppose that we have a system with two blocks, M1 and M2, and there is a string connected between them. These two blocks are resting on a frictionless surface, and we apply a force F to M2. So this system, as you can imagine, is going to move to the right with some acceleration. But let's take a look at the individual forces acting on each one of the blocks. So for M1 we have the normal force with the floor, we have the weight of the block, and the other object that is touching M1 is the string. So you would expect the string to put a force on M1, and because strings can pull but they cannot push, and the string is to the right of M1, you would expect that force to be pulling M1 to the right. For M2, we take a look at the objects touching M2. The table is touching it, so it puts a force N2. There's the force of gravity. There is some external agent applying the force F to M2, and in addition to that we have the string making contact with M2. So that's going to put a force to the left of M2. The force again needs to be to the left since the string is to the left of M2 and strings only pull, they don't push. So I label these forces. The force of the string on M1, I called it Ts on M1, and the force of the string on the block M2, I labeled it Ts on M2. Now since it's one single object that is applying these forces on M1 and M2, you might wonder what's the relationship between those two tensions. Are they related somehow? You might think that they are an action-reaction pair. So is this true? The answer is no. These two forces are not an action-reaction pair for the simple reason that M1 does not interact with M2 directly. Remember that when you have an action and reaction pair that belongs to an interaction between two objects, then the two objects are in direct contact with each other. M1 is not putting a force on M2 directly. M1 is in direct contact with the string. The string is in contact with M2. M2 is not directly in contact with M1. So it is not possible that these two forces that are applied to M1 and to M2 are an action-reaction pair. We can prove it even further by thinking about the forces acting on the rope, on the string. The string is attached to the two blocks M1 and M2. The forces that these blocks put on the string are as follows. The block M2 to the right of the string must be applying a force T M2 on S, and that force must be to the right, since M2 is accelerating to the right because of the force F. If you look at the other side of the string that is connected to M1, M1 has inertia. That means that M1 is going to resist the attempts of the string to accelerate to the right. So M1 is going to pull on the string with a force T M1 on S. So those are the two forces that are acting on the string. Now if the string has a mass m sub s that is not zero, then you can write Newton's second law for the string, which tells you that because the acceleration A is to the right, we should have the tension from M2 acting on the string going to the right minus the tension M1 on S acting to the left. The sum of the forces should be equal to the mass of the object, in this case the string, times the acceleration. So if the mass of the string is not zero and the acceleration we know is not zero, then the difference between those two tensions is not zero, which means that those tensions are not equal. Now if you look at the forces that are acting on the blocks, these forces, as you remember, we call them the tension of the string acting on M2 and the tension of the string acting on M1. They're also not equal. These are the forces that we thought that maybe they were an action-reaction pair. They cannot be equal in magnitude because for sure we know that those forces are action and reaction pairs. M2 on S and S on M2, those are definitely action-reaction pairs. They have the form force of object A on B and the force of B on A. which guarantees that those tensions are equal. If Tm2 on S is different from Tm1 on S, then it follows that Ts on M2 is different from Ts on M1. They cannot have the same magnitude if the rope has a mass that is not zero. This equation clearly shows us that if the mass of the string is not zero, those tensions are not equal. Of course, if the mass was zero, if we could just neglect the mass of the string because it's very light, then it would be true that those tensions are equal. In that case, we could refer to those two tension forces as an effective Newton's third law pair. Another case in which those two tensions are going to be the same, even though the mass of the string is not zero, is of course in the case of equilibrium. When the acceleration of the system is zero, then clearly the two tensions will be the same, provided the string is horizontal. Now for a massless string, then we have found that the tension at both ends is the same. But actually, we can go further. For a massless string, the tension everywhere along the string is the same. It's actually easy to show this. If you have your string, your massless string, and you apply two forces at each end of equal magnitude. Suppose that you cut the string in the middle, and you connect a spring scale. What is the reading on this scale? Well, let me remind you what scales are supposed to do. When you have a scale in a supermarket, and you put 3 pounds of grapes on the scale's plate, then there is 3 pounds of force pulling down on the scale. But that cannot be the only force acting on the scale. If that was the only force, the scale would be falling to the ground. Clearly the scale is connected to, say, the ceiling or some other object, and that object is going to apply a force to the scale to keep it in place. The force should be also 3 pounds, but pointing up. So this is the situation in terms of forces. Of course, the scale reading is 3 pounds. It is not 6 pounds, it is 3 pounds. In every situation where you have a spring scale, there will always be two forces acting on the spring scale in opposite directions. Otherwise, the scale would be accelerating. The reading on the scale is the magnitude of one of those forces. So going back to our spring scale stuck in the middle of the rope of the string, then the force that spring scale is going to apply to the right side of the rope should be equal to the tension, to T, because we know that the mass of this string is zero, also is not moving. So those two tensions must be equal. The force that the spring scale must be applying to the left side of the rope must also be T, same as before. Action and reaction tell us that the right side of the rope is going to be applying to this spring scale a tension T, and likewise for the left side. So the scale has the two red vectors, which are the forces that are acting on the scale. Each one of these forces has the same magnitude T. The scale reading, of course, is going to be T. So whenever you place a device that can measure the tension in a rope, if you place this device in the middle, and there's two forces pulling on both ends of the string, then the device is going to show a tension T. Now we put the device in the middle. Do we get the same result if we stick the device in some other place along the string? The answer is yes. Suppose that we put the spring balance here. The spring scale is going to have to apply a force to the left, to the right side of the rope, a force to the right, to the left side of the rope. Those two forces are going to have a magnitude of T, which means that the scale reading is going to be T. It doesn't matter where you place the spring scale, the reading is always going to be T. So now let's see a situation where we have the two blocks are not moving along a line, but let's say that one block can slide on the surface of a table and the other one is hanging, connected by a string to block 1. So if you let go of the system, the weight of block number 2 is going to accelerate the whole system. The block 1 is going to move to the right, block 2 is going to move down. So block 1 is going to have an acceleration a1, and block 2 is going to have an acceleration a2. Now the string, as it is attached to block 1, is going to put a force on it. Let's call that force T1. The string is attached to block 2, so it puts a force on it. Let's call that force T2. Now because the string, if we assume that the string and the pulley are massless, then it is not very difficult to show that the two tensions must be the same. So the fact that the tension is the same everywhere inside a massless string is true even when the string is not moving along a straight line. This does depend on the pulley being massless also. If the pulley is massless, or if there is no friction between the string and the pulley, then it is true that the two tensions will be the same. This will be a good approximation in many physical applications. So we're going to go with that. The tension along a string is going to be the same. So if the string is non-stretchable, then there is one more thing that we can say about the system. We can say that A1 in magnitude is going to be equal to A2. This is called a constraint equation, an equation that relates the acceleration of one object in the system with the acceleration of another object in the system. Now both of these results, the fact that T1 is equal to T2 and A1 is equal to A2, they have been derived, or they depend on the ideal string and pulley approximation. If you can assume that the mass of the string in your problem is negligible, and also the mass of the pulley, in this particular situation with the blocks in the configuration shown, the ideal string approximation, the fact that it is non-stretchable, will give you that the magnitude of the accelerations is the same. This we can actually prove easily, so let me show you how. Here are the blocks 1 and 2 again. Let's prove that A1 is equal to A2. Let's say that at some time t equals 0, block 1 and block 2 were at the positions indicated by the dashed line. Let's say that sometime later, let's say 1 second later, block 1 has moved to the right and block 2 has moved down. The distance that block 1 moved, let's call it delta S1. So if you look at the string that is horizontal, the segment of the string that is horizontal, you'll notice that that segment of the string between t equals 0 and t equals 1 lost an amount of string equal to delta S1. During that same amount of time, the segment of the string that is vertical gained an amount of string equal to delta S2. Of course, if the string is non-stretchable, the two amounts of string, the one that you lost in the upper part and the one that you gain at the bottom, should be the same length. Otherwise, the string will have stretched or get smaller. So this implies that delta S1 is equal to delta S2. If delta S1 is equal to delta S2, then by dividing by the amount of time, you conclude that the velocity of block 1 in magnitude should be equal to the velocity of block 2 in magnitude. If you take one more derivative, you end up with the accelerations of block 1 equal in magnitude to the acceleration of block 2. This is what we call the constraint equation for this particular problem. Now there is going to be a sign that you might need to use, positive or negative sign, in the constraint equation. A1 in general would be plus or minus A2. What sign you're going to use is going to depend on how you select the coordinate axis for the blocks. I will illustrate that in the next problem.